Welcome to the lab series. This is the first of the 6 labs. This lab deals with the continuous spectrum and emission spectrum. We will talk first about how light is produced, and then how these different types of spectra are produced, then how these experiments will demonstrate these type of spectra. So if you look at the first slide, this shows us the way in which light is produced. If you take the classical model of atom, there is a nucleus and there are electrons going around them. And if you excite the atom, the electron will jump from the ground state to an excited state. This is called absorption, and it cannot stay there for a long time. It will stay there only for 10 to the power of -9 seconds, and then it will fall back to the ground state, giving out a photon. So this is how light is generated. The continuous spectrum, these electrons keep jumping to different levels, and then they will be coming back to the ground state from these different levels completely at random. Because of that, there are no discrete wavelengths or energies in this particular case, and we have all of them continuous. That's what is shown here. When such a light, which is now we can say white light, which consists of all the different colors, if we send them through a dispersive medium, it could be a prism or it could be a grating, one of the two. So if you send that one, you will see that these are distributed into these 7 colors. The red bends the least and the violet bends the most. This is because we said that refractive index is a function of the wavelength. That's why this is dispersed. And if you allow such light coming from an incandescent source and allow that white light to go through a prism or grating, you get this continuous spectrum. You can see the continuous spectrum here. This is spectrum as if all the colors are smeared from red to orange to yellow to green, blue, and violet. These wavelengths go approximately from 750 nanometers on the red to approximately 350 nanometers in the violet. As can very clearly be seen that this spectrum does not have any sharp lines. Compare that with the emission spectrum. This spectrum, we have said, is the fingerprint of the particular element, wherein the electron jumps only to a particular level corresponding to that atom, or levels to that atom, and then fall back, giving discrete wavelengths. That's why these wavelengths are all shown here as discrete lines against a dark background. The third one, of course, which we are not doing an experiment today with that is the absorption spectrum. This spectrum looks like a continuous spectrum, but with certain wavelengths missing. This spectrum is produced when light from a hot gas goes through a cold gas, and the cold gas absorbs certain wavelength, the rest of the light is given. So we will be demonstrating these 2 spectra, the continuous spectra and the emission spectra. So in part A, we will be showing the continuous spectrum. In this one, we will follow the same figure that is shown in the book. We can see this one, that there is a flash lamp here, and below that there is a grating. Here we don't use a prism, we use a grating. As I said, the dispersive medium can be either a prism or it can be a grating. This is the grating, and below this we can record the spectrum. This, when you see the experiment, you will see the continuous spectrum. You will note the different colors, and you will mark these colors, their approximate wavelengths, and then you can compare that with the continuous spectrum chart that we have got. Then we will talk about the emission spectra. This experiment also we will be showing in a little while, and it's important to know that there are certain equations which we can use by which we can calculate the energy of these electron jumps. This is a simple equation which says E2 minus E1 equals to hc over lambda. This is in joules, and in this one, E1 and E2 are the energies of the different levels. h is the Planck's constant, which is given here, and c is the velocity of light, which is given here, and the lambda is the wavelength of this particular color. So this joules, in joules, the energy, the electron jump is extremely small. Therefore, they have given a second unit called an electron volt. A 1 electron volt is 1.6 times 10 to the power of negative 19 joules. It can also be given by one of the older units, which is called the wave number, it is inverse centimeters, and these values can be calculated. So if you look at the experimental setup here, you have the grating spectrograph, and this is of course a small type of spectrograph, very inexpensive one. There are very expensive spectrographs also, and this is the tube in which the element in gaseous form will be there, and that will be excited by a power supply, and this light can be passed through the spectrograph and it can be seen through the eyepiece. We can put an incandescent light next to it so as to illuminate the wavelength, the scale also, which is there inside, and these two together will superimpose one another. Therefore, you can see the wavelengths of the colors which we are seeing. Once you do that, you note down the various wavelengths you are able to observe for a specific tube, and then you will, from the wavelengths, you compare them with the chart, wavelength chart, and from the chart you will see, you will identify what the element is, and from there we'll do the calculations. So first you got the wavelength, and then you do the h, you know the c, therefore you can calculate the energy difference E2 minus E1. From the energy difference, which is in joules, you can connect them to electron volts, and you can also convert them into wave numbers.